For the last session of ACNS this year, we have 4 talks to finish the session. Thank you very much for being here, because I'm sure the speakers will appreciate it. The room is not completely empty. So the first talk will be given by Björn Takman, and he will talk about stateful multi-client verifiable computation.
Thanks, Vela. So, last session of the conference, directly after lunch. I love challenges, so let me try to excite you. So this is joint work with Christian Cachin from IBM Research in Zurich, Esha Ghosh, who's now at Microsoft Research, and Dimitrios Papadopoulos from Hong Kong University of Science and Technology. So the problem that we're looking at is multi-client collaboration in the cloud. And when we say multi-client, what we think about is small number of persons, maybe your friends or family, maybe your colleagues from work, and you want to have some shared resource in the cloud, maybe a calendar, maybe a source code repository, and you want to have that hosted in the cloud in a way that is secure. So we're willing to give up on confidentiality here, but what we want to secure is integrity. So whatever operations you perform on the data, those operations should be performed faithfully, and there should not be incorrect data in the cloud. So all the computations that you do should be correct. Maybe you may be leaking information. The assumptions that we're willing to make is that there's some public key infrastructure available. So basically all the clients do have a signature key. And we work in an asynchronous network model, so there is no upper bounds on the message delivery times between clients and servers, and we do not assume any client-to-client communication. The main reason is that clients might not be online at the same time, and we don't want our protocol to break down in such a situation. So we do not assume that the cloud is correct. So with current cloud outsourcing, if you have like a shared calendar, it's usually if the cloud would be malicious, they would be able to falsify your data, and that's what we want to protect against. On a very high level, we formalize the computation that the parties are willing to do or desire to do as an abstract data type. So very roughly, an abstract data type is described by a function f, which has a state. So the inputs of the function f are the state kept on the server, plus an input or operation that the client wants to perform, and then the output of the function is an updated state and a response of the client. So roughly what you can think, or how you can think about this, is that the clients are one by one going to invoke this function, and what we want to have is that basically they do a computation of this stateful function. And a protocol, in a very high-level sense, a protocol will be called secure if it essentially emulates the access to such an abstract data type, so that whenever a client does such an operation, it will receive a correct response based on all the operations that have been executed with this functionality before. Now, there's one first problem, which is this is not even a complete definition. And the reason is that we have an asynchronous network, we have concurrency, so what does it even mean to emulate these data types if two clients invoke operations concurrently? So this is indicated on this slide. And for instance, you can see that the operation, so the first bullet here is where the operation of the first client starts, the second one is where the operation ends and the client obtains the result. This operation is concurrently to the second operation. Now, if we run a protocol to emulate this abstract data type f, that could mean that either here maybe the first message is delayed very, very long and the operation actually just executes here, whereas this operation executes slightly before, and actually then the protocol would result in operation O2 being executed before O1, or it could result in O1 being executed here, O2 being executed here, and the operations being executed in the other order. So the best we can hope for, this is a terminology from distributed systems, is linearizability, which is defined as follows. If you have operations which are concurrent in this sense, then any order is possible. If operations are strictly separated by real time, like here the first two from this third one, then the third one must execute after the first two. Okay? So very roughly, the definition is if we have a trace of an execution in the real world, But if we then use some reordering on all the concurrence operations, if we then end up with a history that is basically explainable as a linearizable, as a linear execution of this abstract data type, then the system is safe. At least it's as safe as it could be. Now comes the second issue, which is in our scenario, even linearizability is impossible to achieve. And the reason for this is that we do not want to assume any client-to-client communication. So in the setting we see there, say the two clients on the right, they do a computation, they see the actions of one another, and the client on the left does some operations. He doesn't see any effect of the other two clients, and vice versa. So there's two possible explanations. Either the server might, for each of the clients locally, either the server might be honest, and the asynchronous network on the other side might just be extremely slow, so that actually the other set of clients does never execute any operation. Or it could be that the server is malicious, and he basically, what he does is he takes the initial state, forks two substates, and just runs the honest protocol towards the client on the left and the clients on the right, and there is no way for the client to distinguish these cases. Okay, so any protocol, any malicious server, with whatever protocol we have in this scenario, will be able to make this attack. Now the good news is this notion has been formalized as fork linearizability and is actually it's achievable, and it is basically the attack that I showed you on the previous slide is all the server will ever be able to do. So fork linearizability is like linearizability, with the exception that at some point in the execution, or at multiple points in the execution, the server may decide to fork into two or more sets of clients, but then those two sets will have to remain forked and separate forever. Any attack that the server can possibly do will either not lead to any malicious result at all, or it will lead into exactly such a fork, or the clients will detect it. And if the server ever tries to kind of re-merge the forks, or if the clients ever communicate among each other, then they will also be able to detect such a fork. So basically, only in the case where clients do not communicate, there's one possible attack, which is a fork. Otherwise, the notions are more or less the same. And this is usually sufficient in applications, because when clients are online at the same time, they can execute they can share some information and see that actually such a fork happened. A very important tool in these types of protocols is also from distributed systems, it's vector clocks. You can think about vector clocks as follows. Basically, we have some number of parties, here it's 4, and everyone has a local sequence number. It's basically an operation counter. So whenever you locally see an event or execute an operation, you can increase this counter locally. And a time in the network sense is then just defined as a vector of these local times. So what that means is that when I am a client and I do some operation, I will tag it with my local view of the network time. So all of these times are obviously partially ordered, but what a client can make sure is that his local view is totally ordered. So roughly, say you do an operation in the network, you increase your local timestamp because you do an operation and you perform it. And now, after that, I'm performing an operation. Now there's two possibilities. Either I see your operation, then I increase my timestamp based on your timestamp, and they will be totally ordered, but also our operations will occur in a totally ordered sense. Or I might not have seen your operation, then I increase my timestamp, but then our operations have a timestamp that is not totally ordered, and whenever we communicate, we can compare timestamps and figure out that there must have been some kind of attack that made us be desynchronized. Okay, and this is one very important tool in our first very simplified protocol, which just works as follows. The server will always keep the state of the operation and the last timestamp of a client that led to that state, as well as a signature on both the state and this last timestamp. Now, if as a client I want to run an operation, what I do is I tell the server, hey, I want to invoke an operation, please give me the state. The server will then send to me these three values, the state, the time value, and the signature, and I will locally compute the operation. So I will in particular verify that the signature is correct, so that the state has not been falsified. I will check that the timestamp I received is strictly larger than my local view of the time, so it's still kind of in a total order sense. I will then update the timestamp locally at my position, update the state by computing the functionality locally. I will then sign the new state and the timestamp and store the timestamp and send all the data back to the server. So it should be kind of intuitive that this protocol achieves what it's supposed to achieve. So we have integrity of the data because it's always properly signed by one of the clients, and the clients are all mutually trusted. Also due to these vector clocks, we keep a consistency that may be forked by a malicious server, but a forking of the history is all that the server can ever do. This protocol has two major disadvantages. The first one is inefficiency, namely because there's no possibility to have concurrent operation. When I want to invoke an operation, I have to wait until all previous operations have been processed. So if there's one slow client, he will basically stall the entire network. The second one is I have to send the entire state of the computation in every computation step. So this is obviously not a protocol that we want to use if we have computation with large states. We deal with this by a concept called authenticated data types. So very roughly, this is the standard definition of authenticated data types. I use it as a reference. We will use a slightly different one which I show on the next slide. But the motivation of authenticated data types is that in a setting where one party produces information, say he's producing some stream of data, he wants to authentically deliver it to all clients, but maybe he doesn't have the network capacity to do so. So the idea of an authenticated data type is that basically what this writer does is that he stores the information on the server. All clients can retrieve it from the server, but the server is not trusted. So to keep consistency, what we do is we generate a message which we call an authenticator. It's the alpha here. And the alpha is sent by the writer to all the readers, and then they can verify the authenticity of the information they retrieved from the server. So this should be a kind of short value, like length of the security parameter, but independent of the state length. So the type of abstract data type that we use is a two-party abstract data type, where basically what changes is that every client could be either a reader or a writer. There is no separation between the two roles. Otherwise, it's exactly the same. We still update information on the server, then communicate the authenticator between the clients, and use it, or the other clients can use this authenticator to verify the integrity of the data. Just as an example, the best known abstract authenticated data type is just a Merkle hash tree, where basically this corresponds to the data structure of an array, and every field of the array, like A, B, C, D, is first hashed by a hash function, and then we use those values to basically build a tree. So we hash the hash of A and the hash of B to get to this combined value, and so forth until we get to the root of the tree. And the idea here is that if I want to read that, if I want to read from that tree, for example, I want to read the value A, then what I get from the server as a proof of integrity is, if I want to read the value B, what I get is the value B, the hash of value A, and the hash of CD. Because if I do this, I can first hash B, then hash this hash and this hash to compute this value, then I can hash this and this value to compute this value, and then I can compare it with the authenticator I received from the server. Okay, so that's the most widely used abstract data type. What we do in the paper is that we give a definition in terms of 4 algorithms. So there's an initialization, then execution of an operation by the server, the verification by the client, and finally there may be a refresh necessary by the server using some information computed by the client. This is very similar to some works that have appeared in the literature before. The main difference is that we have very general definitions, so our algorithms can be deterministic or probabilistic. They can generate such an update token which application is sent to the server or not. So basically they should be covering most abstract authenticated data types from the literature. What we then do is we also provide security properties, and they are very similar to the ones you might have seen in Luca's talk on Monday. So what we want is, first of all, correctness. Basically, correctness of an abstract data type is just defined as you have a client, defined as an adversary in the definition, that just does operations, and then we check whether the operation is done correctly. The next one is soundness. It's basically the security against the malicious server. So we allow the server to basically generate potential proofs, check them with the client, with the verification, and the server wins if he produces a proof that verifies but actually is not valid. And finally, the last definition we need in order to prevent trivial instantiations is succinctness. So the length of the authenticator should only depend on the security parameter and not say on the length of the data type, because otherwise I could just send the data type as the authenticator, and that wouldn't really save anything. So one main technical contribution in the paper is that we generically instantiate abstract data types using verifiable computation. I'm not going to go into details of verifiable computation. We built on a scheme called Pinocchio, but I want to explain to you the main idea behind the construction. So verifiable computation is basically you have the function f, which is a function from x to y, and the client wants to compute f of x, so it wants to compute the value y, but maybe it doesn't have sufficient computation capabilities, so what it does, it sends x to the server computes the y, and also computes a proof of correctness, sends it back to the client. The client verifies, this is a constant time operation, so it may actually be faster than computing the entire operation by himself. So, one very important property of this scheme is that it supports something called offline-online verification. And the important part is here, which is this phase called the offline phase, which only depends on the verification key and the X. It does not depend on anything else. And second, the online phase does not depend on X apart from this thing here. It depends on whatever this algorithm outputs, but it does not depend on X beyond that. So this was actually seen in a work by Fiore et al. At CCS 2016, and they said, wait, we can use this in order to outsource the computation on X onto the server. So if X is maybe not even stored on the client, because it's a huge pile of data, we can actually outsource the first part of the computation, this offline part, to the server, have the server compute this part as well, and then have the client just verify the online part. So the basic idea is that there is an additional proof here. MXP stands for multi-exponentiation. The reason for this is that this hash function is basically a multi-exponentiation, and we will have to prove a consistency here. So basically the client starts from a hash value which corresponds to this big state stored on the server. And now what I want to evaluate is the function just on this state x. So what the server now does is that he computes the function, he also proves that he does so correctly, and second, he does this offline computation that we now outsource to the server. But this may have been a malicious computation. So what we also ask the server to do is to provide a proof that actually this value z he created corresponds to the pre-image of this hash value h. So we have this additional proof psi here, and we send back to the server, to the client, the value z, the output y, the proof pi for the verifiable computation, and this proof that we computed the first half of the verification correctly. Now what we do is we basically do the same thing for the output. Okay, so that's the entire magic behind our construction. So basically, the server has the state x, but we want to be able in this abstract data type to update this state, right? I mean, otherwise we cannot have a stateful computation. So what we do is that the client, okay, can send an additional input and receive an additional output. I've just dropped that for simplicity of the letters here. What the server now does is he computes the function, he computes the hash of this new output, so we're now at this yellow hash. This will be the next hash that the server, that corresponds to the new server state. We then prove the verifiable computation. We prove the offline part for both the input and the output, resulting in this green and the yellow Z. And then we prove consistency with the hashes for both the green Z with the green hash and the yellow Z with the yellow hash. So roughly speaking, what we do is we know that we have the hash, the green hash here corresponding to the X. Using the green proof, we kind of provide this authenticity to the green Z. Then the computation, the verifiable computation uses the green Z. It kind of provides the correctness for the yellow Z, and from the yellow Z we go to the yellow H. And now the client can verify all these proofs and knows that the yellow H is the hash of the new state. Okay, so on a very high level, you can also see this as first computing the function and then verifiably computing the function that verifies whether f of x equals y. And if you write it like this, then it becomes clear that what we do is just an operation in which we outsource the computation on the inputs to the server, and this is pretty much the same which this scheme of Fiore et al. Solves for us already. So this is roughly how you can see our construction. So while the original papers on verifiable computation, they were able to verify computation just from X to Y. The paper of Fiore et al. Can be seen as verifiably computing functions that depend on a state stored in the server and an input by the client. They compute an output to the client. And our verifiable computation, it can also update the state to the server, get an input from the client, and provide an output to the client. Okay. We then use this in a kind of obvious way to instantiate an abstract data type. So in the initialization, what we do is all the key generation for all the proofs, for the multi-exponentiation proofs, and the compute a hash of the initial result, and that's the initialization of the data type. In the execution, we do exactly the scheme that I just described. In the verification, we have the client verify as described on the previous slide, and the refreshing is basically just replacing the old server state with the new server state. So we then include this into a protocol which now works almost as the protocol that we had before, just that we shift the computation from the client to the server, and therefore we can also just store the state at the server. So the server keeps the state of the abstract data type, the last timestamp that we've seen in the previous protocol, and also a signature on the previous authenticator. Now if a client wants to invoke an operation, the server will authentically compute the operation that the client wants to compute and send to the client the previous state, like the previous authenticator, the previous timestamp, the signature on the two, and the correctness proof for the authenticated data type. The client then verifies pretty much the same things as before. Just additionally, he also verifies the abstract data type and then computes a signature on his new timestamp and the new authenticator that he received from the verify function, and then he sends that data back to the server. So the protocol works pretty much like the one before, but it has much more efficient communication. The protocol, so what does it achieve? If the server is correct, then we actually get full linearizability. If the server is malicious, we get fork linearizability. The complexity of the protocol is, as you've seen, it's 3 messages, where the messages are of length O of n, that is the timestamp. And also, basically, we send the timestamp, the signature, and the ADT authenticator, so it depends on how large this is for the particular scheme. What we can also add is support, we didn't do that in the paper, support for commuting operations, so that certain operations of the clients could be computed ahead of time, even though not all clients verified their computation up to that point. So this is based on a paper by Christian Cachin and Oya Orimenko. Their protocol is called COP. I think it was published at PODC 2014. So just a very quick glimpse on related work. It's impossible to cover all the related work because it's distributed systems, abstract data types, verifiable computation, all that. So it's just focusing on the protocols here. So the fork linearizability was introduced in this paper in 2002, where they focused only on file storage, not generic computation. Then Cachin et al. They improved the protocol in terms of efficiency, implementing read-write registers. And then this paper here from 2009 called The Blind Don't Have That was the first one to actually implement generic computation. The computation itself was performed on the client. So every client had to replicate all operations. This is similar in the POTC 2014 paper by Cachin or Remenko, where they add this better support for commuting operations. Then there is a protocol which is already based on abstract data types. It's not really analyzed in an provable security sense, but this is the main motivation from which we started. And what we do in this work is a slightly simplified protocol, but we prove it secure, and then instantiating the abstract data types in a very generic way, whereas here in this protocol what they were using is basically just Merkle hash trees, and therefore basically implementing a cloud object store, whereas this protocol supports generic computation.
Any questions?
Did you try to implement this, or is it just theoretical?
No, we didn't implement it, and the main reason is, as it is now, based on the verifiable computation schemes, it's probably not practically efficient. The reason is that the hash function that we compute there is a multi-exponentiation, and basically we have to exponentiate every single part of the input to the state of the data type. So I just did some back of the envelope computations. It should be kind of efficient until a state that is maybe a few megabytes, but then it becomes too inefficient. So as soon as we don't have more efficient verifiable computation schemes, using it in this way is not quite practical yet.
Thank you. Any more questions? If not, then let's thank the speaker again.
Thank you.
Move to the next presentation. Our second speaker is Sunil Park, if I pronounce it correctly, and she will talk about VeriCount, verifiable resource accounting using hardware and software isolation.
Hello everyone. Sorry for the wrong introduction. I am Shruti Dokle, the first of them.
Oh, sorry. Okay.
From National University of Singapore, and today I'll talk about how we can verify resource accounting using hardware and software isolation. So the main motivation for this work stems from the immense amount of outsourced computation, with cloud services providing you computation with their resources instead of buying lots of resources on your local machine and then computing. What you could do is just request for computation, and the services will use their CPU time, network bandwidth, IO bytes memory, and then just return you the output along with the bill at the end of the month. This is a quite common scenario that we, at least as PhD students, observe while doing our experiments at the end of the deadline, estimating a bill for our experiments, and at the end the bill is something unexpected. Essentially, the main purpose that this model is becoming popular and working is because of the pay as you use. The cloud services offer that they'll charge you for whatever resources you are using, and nothing more or nothing less than that. But for this, the main property that we need is verifiable resource accounting. And why is that? Because in case of a malicious cloud provider, what you might do is try overcharging the users for the resources that they have used. And on the other hand, malicious clients can try to undercharge themselves, that is, make sure they compute more with less resources that are used on the cloud. And this problem is for real. Researchers have shown that you could actually, the clients could use free CPU time for EC2, and rack space was overcharging for storage, either because of some bugs in software or some wrong logic in the accounting itself. So what do we need to avoid this? What we need in real life is a billing system that's based on a neutral backdrop that covers any problems such as misattribution, incorrect billing, or false accounting. This requirement becomes more difficult with container-based virtualization, such as Docker systems that are sharing resources at an even finer granular scale. So in this work, we try to ask the research question that is it really possible to build a reputable billing system for the cloud services, which is fair for both the clients and the cloud providers, where the cloud providers can send you a bill and the clients can refute the bill if they feel that it's been overcharged, and the cloud providers can actually give guarantee or give proofs that the bill is accurate to what the computation was requested. In my work, my contribution will answer the question that we've asked here, but with three major contributions. The first contribution is of actually designing a self-accounting logic that isolates the accounting engine from both the untrusted operating system, which might be malicious, and from the client's application, which might also be buggy and try to undercharge. The second main contribution is an end-to-end system called as VeriCount, which we provide for any application that you want to run on an untrusted cloud server, which has low TCB using trusted hardware and is based on software fault isolation mechanism. Lastly, what we show is that our transformed applications, which have this verifiable resource accounting mechanism, actually incur a very small overhead of just 3.62% as compared to running the vanilla benchmarks. Then let's jump into the main problem and see why resource accounting is really important. We work in a threat model where both the cloud provider can be malicious. Their operating system that it is hosting, or even the hypervisor, can be compromised. It can have bugs that can be exploited and hence can lead to overcharging. But the cloud provider is restricted. That is, it cannot generate any new inputs to what resource computation you have requested. On the other hand, the client can be malicious. He has this code that he is requesting on the cloud server. He can input some bugs or vulnerabilities in the code which will later trigger while executing and can result in undercharging or manipulating the accounting summary. What we don't handle here is denial of service from the cloud provider. If the cloud provider does not allow executing the requested computation, then this is what VeriCount won't handle. And lastly, as I mentioned before, the cloud provider is not allowed to generate inputs on the fly, because if he can do that, he can just create infinite number of inputs and create a very large resource usage summary for the client. So let me just clarify the problem definition very briefly. What we do here is a series of interaction between the client and the cloud provider. The client and the server first agree on an execution policy file, which is essentially a tuple of three terms, which includes of P, which is per resource pricing scheme, like what is the price for the CPU time, for the network bandwidth used, memory, etc. C is the crash recovery limit, like when I have requested for a virtual machine on a container to host my application, for example, a machine learning module, training a machine learning module. How many times can the server crash due to legitimate bugs in the machine learning module or in the code? And how many times can the server created, reinstantiated because of errors at the server side? And lastly, T is the time for the OS response. If the container requires any services from the OS, how long can the OS take to respond? Once this agreement is established, the client sends its application along with the inputs. For example, whatever is my machine learning model with the training data set, I'll send it to the server. And then the server will execute it and send me the resource summary, which is RA, along with the bill corresponding to that application, which is BA over here. And what we want to achieve at the end is a verifiable resource accounting, that the client should be able to verify that the bill which is corresponding to this application actually corresponds to the resources that are used by my application for the inputs that I have provided, and nothing more or less, based on the execution policy that was established before. So what is there currently that's happening with the cloud server and why is it not sufficient? The current approach that the cloud providers use is that the resource accounting logic or the main code that calculates how much resources, what is the CPU or network bandwidth your application is using, that's implemented in the OS itself, that's implemented in the compromised or buggy operating system, which we don't trust in the first place. So here what the operating system can do is, because the resource accounting logic is there, it can tamper the memory and just clearly overcharge it. So we want to avoid this. So previous research has identified this problem, that the accounting logic is with the compromised OS, which is not a good solution. And what they have proposed is isolating this resource accounting logic from the OS and putting it in a trusted region. So here the shaded area is the untrusted region and the white area is the trusted containers. So what you do is, instead of putting the resource accounting logic with the OS, you remove it and place it in a trusted container. Now what it becomes is, it acts like a trusted observer. Nobody can tamper the information that the trusted observer is calculating, that is accounting. So the OS, even if it wants, it won't be able to tamper it. Whatever the application is actually using, the trusted observer or the accounting engine will actually calculate and note that. So this guarantees that, okay, at least the OS is not able to go and manipulate or arbitrarily overcharge. But does this solve the problem? Is isolating the accounting logic from the OS sufficient to get what we want? The answer is no. The OS can still do an attack called as resource usage inflation attack. And why? Because there is still execution dependency on the OS. Even if the OS cannot directly transfer the resource accounting logic, it can create new instances of the application because the container management is still with the OS. What the OS can do is perform a series of attacks. Ideally what we want is the benign case, where my application A is run over the input I and I should have a resource usage summary of RA. But what the OS can do is, it can reinstantiate my application in different containers, for example A prime, A double prime, and provide the same input. Now what the OS or the cloud provider will tell me is that your application required 3 times the resources. Similarly, it can provide input replace, it can do arbitrary halts, just crash the container and then restart it again, making it use more resources. And such other attacks are possible. So even if we have isolated the trusted accounting logic, there is still execution dependency on the OS. So what do we do for that? In VeriCount, we solve this exact problem by using an approach called as self-accounting. Here, unlike the previous research, what we have done is the resource accounting logic is tied to the container itself. Every application will do its own accounting. It's tied to the atomic execution unit. And how does this help? This essentially shifts the accounting logic from ring 0 to ring 3. Now, whenever the application is executed multiple times, it can essentially record that this particular application was instantiated 3 times. And then you can detect RUI, like resource usage inflation kind of attacks, and protect against overcharging. So this simple idea of tying every resource accounting engine to the application itself, instead of having a common trusted observer, has solved our problem of resource usage inflation attacks. But has it still solved the problem of undercharging from the client provider? The answer is no. If you observe carefully, what self-accounting has done is it has created a client code dependency. Now because the application and the resource accounting engine are in the same container, in the same memory region. So now the application can override the resource accounting logs and can try to undercharge itself. What we want is that the accounting engine should be isolated from both the OS and the application. And how we do this is using software fault isolation. So what we do is the application will not be able to directly do store and load from the resource accounting engine memory, essentially separating the resource accounting engine from both the client application code and the operating system using hardware isolation and software fault isolation. Let me give a quick overview of how VeriCount works at the end-to-end. There are 3 main components in VeriCount. One is a compiler, a static verifier, and a post-execution analyzer. Okay, so this is how it works. The first is the compiler, which is an untrusted piece of software. You don't have to trust it. It takes in the application whatever you want to run on the cloud. For example, a machine learning platform or a piece of code, and it transforms it. Essentially, instrument it such that every time it uses CPU or it uses network bandwidth, they'll create a log. The transform code is what we call as VeriCount enabled sandbox application. It will have a resource accounting engine in itself, which will be sandboxed. Once the application is created, we have written a verifier which will run in a trusted region on the cloud server. So what I will do, I'll have this transformed VeriCount application and send it to the cloud provider and ask the cloud provider to run it for me. The cloud provider, however, does not trust it directly because I have used a compiler which nobody has guaranteed for. So it will use our verifier in an isolated memory region and verify that the application that I have transformed essentially does correct accounting. Once the verifier outputs yes, then the cloud provider will actually go ahead and execute the application. The executed application will then create resource accounting logs using a resource accounting engine within the application. And these logs will then be sent to the post-execution analyzer along with the file, which is our execution policy, and a bill which the cloud provider thinks is the right bill for this application. The analyzer will take all these three as inputs and will verify that the bill that the cloud provider has provided is essentially the one that corresponds to the resources and the execution policy that they have agreed upon. If that is true, only then the analyzer will go ahead and forward it to the client. Otherwise, it will clearly tell out that no, there is a discrepancy between what the cloud provider is providing and what the application recorded during the execution and the execution policy. So this essentially gives us a win-win situation between both the client and the cloud provider. And the main building block of our system is a trusted hardware called as Intel SGX. We use several properties from SGX that enable us to actually design our accounting logic. The first and the important property that we use is enclaved execution. SGX essentially allows you to create isolated memory regions that are hardware guaranteed. Hardware isolated. Essentially, what will happen is this application entirely will be running within an enclave, which is hardware isolated, and there will be resource accounting engine within this enclave per application, attached per application, which will again be isolated with SFI. The next property that we use is of monotonic counters for each enclave. This, what gives us is essentially every enclave or every application will be attached with a unique identity. So whenever the OS tries to create multiple instances, there will be multiple identities that will be given to this application. Whenever I as a client send an application to the cloud provider, I will be notified of this unique identity for my particular application. So when the cloud OS tries to do some resource usage inflation attacks by doing multiple instances of the same application, the resource accounting log essentially at the end will have different IDs, and the post-execution analyzer can detect that the same application is being given different identities. That means there has been an execution replay attack. So here, monotonic counters is the key property from SGX that we use to defend against those attacks. This also defends against arbitrary halts, which is again another version of instantiating the same application again, but while shutting down in halfway the previous execution. The third property that we use is the ability to create true random number generator from SGX hardware. With this, what we do is we try to avoid input replay attacks. Every input that the user has provided genuinely is given a random number to it. And every time the user wants to rerun or actually perform an execution of the same input again, it will increase the counter and attach a random number to it. So that's why the freshness of the inputs is generated. Whenever the OS tries to do a replay attack, what it will do is it will replay the same random number as an input to the application, which will be detected by a post-execution analyzer. The second last property that we use is the trusted elapsed time. Essentially what it gives is, using SGX hardware, you can calculate relative trusted time. So You can send an instruction to the hardware, ask for the current time, and then after some time you can again create and run an instruction and get the elapsed time. This is a very important instruction or a property from SGX that allows us to first detect against attacks that the OS tries to slow down by responding to its services. And later also we'll use the same property to actually calculate the CPU time that our application is using. And lastly, we use remote attestation to verify that the enclave code that the application is running is essentially the correct code that the user expects. So let's look into the resource measurement techniques for actually measuring CPU, network bandwidth, I/O, which you will be charged for by the cloud provider. So the first is CPU elapsed time. Ideally, what EC2 does or what Google Compute Engine does is they charge you per hour or per minute. That is, once your virtual machine or your container is up, how many hours was it or how many minutes was it running. It doesn't matter if you were actually executing something. If you have invoked it, then it will just calculate until it's been shut down. In VeriCount, what we do is we even calculate at a finer granularity and we measure in seconds using the SGX trusted elapsed time, which I just mentioned. And how we do this is, in SGX, whenever the application wants to invoke a service or whenever it wants to give the control flow to the operating system, it will have to make an E call, like an enclave call, and an O call, which is like an outside call. So we keep a track and we instrument at these E calls and O calls. Whenever the application goes outside, we will start the timestamp, and whenever it comes back in again, we start the timestamp again, and so on and so forth. So essentially this gives us the time, how much CPU time is spent while executing the application itself. Similarly, for network bandwidth, what we do is we account for the bytes that was service that the application has to use. It has to perform an O call to the operating system. So even for network services such as send or receive, it has to go through the operating system. So our VeriCount compiler will intercept at these file system, network system calls, and will make sure will calculate how many bytes are being sent and write it down in the output logs. Similarly, for I/O, it will keep a track of the file system calls. And for memory, SGX allows processor reserved memory of either 32 MB, 64 MB, or 128 MB. And right now, there is no support for actually calculating page faults, but the SGX next version allows you to even make sure that the application knows how many page faults are happening, which we could use to calculate what is the amount of memory that my application has used. Lastly, once the entire system has been designed, we have evaluated it and implemented it using LLVM. The key steps during the implementation were actually having these API insertions at the interfaces, at the file system call, network calls, whenever the enclave makes a switch to the OS service, and sandboxing the resource accounting engine within the enclave. The TCB is just as small as 542 lines of code, which includes our verifier, analyzer, and the accounting engine, which are all trusted. And this excludes the Intel SGX SDK, which also we trust because of all the features that I discussed before that we use from the SDK. And the VeriCount compiler, which runs outside the trusted zone, is 872 lines of code, which essentially does the instrumentation for your application. For experiments, we used benchmarks, which is Specs CPU in 2006 and an H2O web server. These were ported to SGX-based system using this version 1.8 of SGX SDK. And lastly, we evaluated with two main goals. One is, what is the performance overhead that our transformed applications incur as compared to just running vanilla applications, and how the cloud provider does accounting at this moment. And second, what is the accuracy of our measured resources as compared to the current approach of measuring CPU time, network bandwidth, and other resources. So in terms of performance overhead, what we observed was, on an average, we had small overhead of 3.62% for all our applications that we transformed, as compared to running them just within an enclave. So as compared to taking an application and running it in a secure container, also enabling the additional facility of verifiable resource accounting incurs you an overhead of just 3.62%. And in terms of the accuracy of the measured resources, you could see that the user time is essentially the application time that is that it takes the amount of CPU. And the first column, this OS, is what the OS measured the CPU time, and this is the VeriCount measure. Because the VeriCount uses SGX trusted elapsed time, we could just measure it in terms of seconds and not fraction of seconds. But if you see, we are almost equal for all the applications. Then we also measured the amount of IO bytes and IO calls that were made, and those were exactly same as compared to using one of the OS approaches or the current approaches to measure IO bytes. Next, for measuring bandwidth, what we did was we calculated the data that was transferred over the network to request static web pages using our H2O web server application, and we compared it with using a tool called NetHawks. So NetHawks, what it does is calculates the network bandwidth and the amount of data that's being transferred with your application. So what we observed was, as compared to VeriCount and NetHawks, there's a difference of only 0.66%. And it's almost, it guarantees, it gives you a verifiable guarantee that this is the amount of data that was being transferred. In conclusion, what we saw was that verifiable resource accounting is actually a challenging problem because of resource usage inflation attacks from the OS and client code dependency from the client application. So you want to keep a balance between both the overcharging and undercharging. Secondly, combining both hardware and software isolation is a promising direction rather than just using one of those approaches. Like just using SGX, what we observed was not sufficient to guarantee what we required. Lastly, we present our end-to-end system called VeriCount that provides resource accounting with minimal performance overhead of just 3.62%, a low TCP of 542 lines of code, and a very high accuracy for measuring all the resources. Thank you. Any questions?
Any questions?
Do you have a way to measure, like, if the operating system tries to do something bad, like you ping per minute, and then so the operating system will slow down I operation on purpose?
Yes, so that is that is why we have the threshold, like the T, which is slowdown of the OS services in the execution policy. The OS can genuinely slow down like for a few seconds. But if it tries to slow down above that, above a threshold that's an established execution policy, then you can detect that there is some attack that's happening. Or the other way that we propose is, for all the OS time that is required, like for I/O or anything, you keep a fixed amount of charge, so that irrespective of how much it is, the OS won't go beyond a particular threshold, because there's no point in that.
Any other question? No, let's take the answer. The next presentation will be given by Suyash Kandeli, and he will talk about message locked encryption with file update.
Thank you for the introduction. Today I'm going to present my joint work with my supervisor, message locked encryption with file update. And here first we will see the introduction, followed by the problem statement, our work, the comparison with the existing schemes, and the references. So what basically a deduplication is, suppose Bob comes up with a file, a big file, say a movie, and he wants to store it to the cloud and get rid of it from his local machine. So he will take the help of the cloud manager and he will store it on the server, on the cloud. Another user, Alice, comes up with the same movie and she also wants to do the same, and she uploads it to the file, to the cloud. Many users may do the same and fill up the whole cloud. At this point of time, if any other user comes with an identical or a different file from these, he will not be able to store this data. But what the cloud manager would try to do is, he would try to maximize his financial gains. by giving more space to more number of people here. So he would employ a method in which he will attach a file which will be called as owner's list, and here he will be attaching the identity of every user who is owning this file, thereby clearing all the other copies of the file. Now the cloud has enough space to store any file. This was a simplistic setting where all the plain text all the files were in the plain text. It's visible clearly, and therefore the cloud manager can easily identify the identical files. But suppose if everybody comes up with their secret key and they want to encrypt their file before they upload it. So in this case, the cloud manager will not be able to identify that the files are actually identical. So we need a mechanism in which identical files should generate identical keys, thereby making identical ciphertexts. And since now the ciphertexts are all identical, the cloud manager will be using the same formula as before. So deduplication is basically removing the replica of same encrypted file without compromising its privacy. It requires a method to encrypt identical files in identical ways. It is deployed in Google Drive, Dropbox, Bitcasa, etc. with the solution message block encryption, MLE. MLE is a symmetric encryption scheme in which the key required for encryption and decryption is derived from the message itself, thereby achieving privacy and integrity. Its applications are in deduplication, play-as-you-pay video, hierarchical file sharing, and many other protocols. The state-of-the-art requirements for MLE are as follows. The first one is protection against the fake ownership claim, which is realized by using proof of ownership POW functionality. Here our basic assumption is that the adversary may know the identifier, or better, the tag, but not the plain text or the ciphertext. And the second assumption is that the files cannot be produced from the identifier. Here, our cloud will be, let's take an example that our cloud stores this file with the identifier, and there are some users who own this file. So on producing the same identifier, these clients should be able to access this file from the cloud. But if some attacker has just gotten access to the identifier and he tries to access this cloud, if he does not own the file, he should not be able to access this file on the cloud. The second requirement is update data on the cloud, which is realized using update functionality. Here, suppose some users share one file and the other user shares another file, and this user wants to change his data, and then he should be able to get the access for this file rather than modifying this file, and deduplication should also hold. So Zhao and Chow proposed UMLE in Asia CCS 2017, which is efficiently updatable block level message block encryption, satisfying these four functionalities of update, decryption, encryption, and proof of ownership. The ingredients used here are block level message block encryption and Merkle tree. We see the execution of encryption in UMLE. Suppose we have this big message, we break it into several blocks, and we perform BLMLE on each of these blocks to get the corresponding ciphertext and the key. We then combine the keys to form a new block, and we encrypt them until we get the master key and all the ciphertexts. This is the Merkle tree construction that has been used by Zhao and Chow in this construction. The decryption works as follows. We have all the ciphertext and the master key, and we decrypt the ciphertext C7 using the master key to obtain all the intermediate keys. And this goes on until we get all the blocks of the messages, and then we combine them to get the entire message. The most unique feature of UMLE comes here with the update functionality, where the user wants to change the message corresponding to the ciphertext C3, and he has only the master key and the ciphertext. So here the user will actually decrypt the message to, he will decrypt the ciphertext to obtain the message M3 and a few intermediate keys, and then he will change the message to M3 prime, the new message, and again encrypt it in the same fashion. Here he will be using the new key K3 prime and the old key K4, the old key K5 and K6 prime, and then finally get the new master key. So here we see that log of number of blocks will be updated. This is the distinct feature of UMLE which gives it a boost of updating file at a very quick speed. But the problem here is there is a necessity of using BLMLE in this construction, which leads to inefficiency. And also it has a huge storage requirement. As we have seen, there are log many number of ciphertexts introduced new, which is not suitable for several practical implementations. Therefore, we come up with a new primitive, which is file updatable message log encryption, FMLE, which is actually a special kind of MLE with update and proof of ownership functionality, but is more generic than UMLE. It finds its application in the deduplication protocol with update functionality. The definition of FMLE includes the 5 functionalities for encryption, decryption, update, file and tag, and proof of ownership for prover and for the verifier. The correctness concerns are key, tag, decryption, update, and proof of ownership concern. The security concerns are given by the privacy games PRBCDA, which is chosen distribution attack, and integrity by the tag consistency and the strong tag consistency, context hiding, and proof of ownership by uncheatable chosen distribution attack. Here is the formal definition of UMLE, which is given in even more detail in the paper, and I'm not going into the details. This is the deduplication protocol, and we are looking at the upload protocol in the FMLE setting. So here the client has the message M, and the server has a database T in which he stores all the ciphertext and the tags. The client has the message M from which it generates the key, ciphertext and tag. The client retains key and the tag with itself, and also gives ciphertext and tag to the server. Here the server goes on for the POW, proof of ownership protocol, in which it computes a challenge queue and sends it to the client. The client generates the corresponding proof P and sends it back to the server. If this proof is verified correctly, then there is corresponding action for saving this file on the cloud. Otherwise, it results into an error. The download protocol is pretty straightforward and simple, where the client has tag T and key, which was stored in the previous protocol, and now it demands for the ciphertext corresponding to tag T. If the server checks that the client is the owner of tag T, then he gives back the ciphertext, which is decrypted and verified here, and accepted by the client if it is not altered. This is the update protocol, which is a kind of hybrid of download and upload protocol, where first the server gives back the ciphertext, and then the client updates the ciphertext and sends it back to the server. Now the server deletes the previous ownership and again comes up with the POW for the new ciphertext C prime. On successful verification of this proof, the client gets the access to this file. Here is our first construction, RAVD1, which is inspired from the design of FP hash mode of operation designed by Paul and others, in which we use permutation, which is easy to invert permutation, and we break the message into several blocks of length lambda. Here the permutation used is of size 2 lambda, and we encrypt from left to right. To obtain the ciphertext C1, C2 up to CL-1, and these two values u prime, v prime, the tag and the key. The decryption operates in just the reverse direction, where key, tag and the ciphertext blocks are supplied to obtain the message. The verification takes place at this position, which is a very subtle point. To update the ciphertext, which starts changing at this location, we need to decrypt the function. We need to decrypt the ciphertext only up to this point, and then we re-encrypt it. And therefore, we need a partial pass and not a full pass. And this updates our new key, our tag, as well as the ciphertext. This is the proof of ownership for prover function, where we need to calculate the proof, which is C prime n here, for the proof of ownership functionality. This is our second construction, RAPD2, which is inspired from the design of APE authenticated encryption, whose one of the designer is right in front of us. And this also works on the same principle of encryption from left to right and the decryption from right to left. This is also a very important functionality which gives us a huge efficient construction. This is the update functionality and the POW for prover function. Now, there are some critical points about RAPD1 and RAPD2. The first is its unique property of reverse decryption. The second is it is based on easy to invert permutation, and to the best of our knowledge, it will be potentially useful in IoTs and RFIDs, and it would be easy to realize in hardware. It has a small overhead of storage, and since it is randomized, therefore it is not vulnerable to dictionary attack. It has one-pass encryption and decryption functions, and on an average half-pass update and proof of ownership functionality. Here is the comparison table for FMLE schemes, where the first scheme is actually given by the Dosser et al. In 2002, which we have modified to suit our purpose. The second and third schemes have been taken up from the paper of Bellare Kirvidi 2013, and we have modified them accordingly to suit FMLE. This is the paper by Zhao and Chow 2017 and our work, and we actually obtain much better results for the passes required in the different algorithms. Also, the space required is minimal. Although we lack the STC property in our construction, but any randomized MLE does not support STC property. But we are secure against the dictionary attack. So here we are better than this. So the main point is that FMLE supports more constructions and provides much more flexibility. That's it. Thank you.
Thank you.
Any questions, please?
Any questions?
Why did you go for permutation-based design?
We found that most of the designs that are coming today are permutation-based, and from some of our knowledge, we came to know that permutation-based constructions, permutation is easy to implement in hardware. So that's why we thought of using permutation.
Are you the only one? Are you the first permutation-based, or there are already?
No, there are already some permutation-based constructions, but they don't have as unique property of reverse decryption as these two constructions had. So that's why we could come up with only these two designs. Maybe in future we can come up with some more designs. Thank you.
Any more questions? If not, let's thank again. And we have one more talk for today and for the rest of the conference, for the whole conference. Okay, so the last talk will be about Dogfish, the decentralized optimistic game theoretic file sharing, and it will be given by Untitled Chapter.
Hello everyone, I'm Untitled Chapter from Koç University, and this is joint work with Semi Kamara from Brown University. So I want to thank the organizers. Usually the last talk is picked such that you wouldn't want to leave early, so I hope to live up to your expectations. I will present Dogfish, decentralized, optimistic, game theoretic file sharing. So our scenario is the peer-to-peer file sharing scenario, and why do we care? Because BitTorrent uses the most uplink bandwidth in the internet. And our goal is to minimize average download times or maximize uplink bandwidth utilization. So this is called achieving social welfare. And we want to achieve social welfare in a decentralized peer-to-peer setting. What's the problem? The problem is with the selfish peers. They may act as free riders in the system, causing unfairness. We want to prevent this, so fairness is also a design goal for us. And they may cause starvation in the system. We also want to prevent that one. So to better understand our scenario, let me describe BitTorrent in a little bit more detail. So in BitTorrent, we have a client who wants to download a file that is made up of blocks, or alternatively pieces, blocks for our purposes, they are the same. So the client first starts by downloading what's called a torrent file. This torrent file contains hashes of these blocks, and also the address of a trusted third party called the tracker. So the peer connects to this tracker, obtains a list of other peers in the system, and then starts forming peer-to-peer connections. Now, some of these peers have already downloaded the whole file, and these are called seeders. Some other peers are still downloading the file, and these are called leechers. BitTorrent proceeds in two stages. So first, there's an announcement phase. Each peer announces to each other peer the list of blocks that they own. So each peer announces to each other and collects announcements of other peers. Once the announcements are completed, the peers pick other peers to start the exchange phase with, and now they can start downloading these blocks. Now, this announcements in BitTorrent is also called piece revelation. So each peer is supposed to send this list of blocks owned to the other peer, and BitTorrent assumes this piece revelation is done in an honest manner. But a selfish peer may choose to over-report. So I can report that I own a piece even though I don't. And why? Because an over-reporting peer may appear more attractive to other peers. If I have many blocks, many other peers would want to connect to me. Similarly, a selfish peer may choose to under-report. So I may not report a block even though I own it. And again, this may gain some strategic advantage for that peer against the rarest first heuristic of BitTorrent. But of course, if many peers are under-reporting, this will cause starvation in the system. So we want to prevent over-reporting and under-reporting. Now, before switching to our solution, I want to describe some preliminaries. So throughout this talk, I will assume all of us know what's a Nash equilibrium, but I will mention what's a computational Nash equilibrium. So in this setting, any strategy can only be negligibly better compared to the equilibrium strategy. And this is usually done by breaking some underlying cryptographic primitive. Consider, for example, a protocol that performs encryption and then some exchange of keys. Now, consider the following alternative strategy. Rather than following the protocol, the peer breaks the encryption and therefore doesn't need to exchange the keys. Now, this alternative strategy can only be negligibly better than the protocol strategy. Why? Because I have only a negligible chance of breaking the encryption anyway. The other primitive we are going to employ will be a static proof of storage scheme. Now here we are going to assume that the creator of this torrent file in addition to the hashes of blocks, is going to put these tags used for the proof of storage scheme. And we need the scheme to be publicly verifiable, such that there is no secret employed during the verification procedure. And the peers will act as both provers and verifiers. Finally, we will need a fair exchange protocol. Unfortunately, fair exchange in general is impossible without a trusted third party, but we are going to be in the optimistic setting. So the trusted third party will be involved only if there is a dispute. So it will not be involved in every exchange. So our approach is going to be where cryptography meets game theory. So our strategy is going to follow these two steps. First, we are going to argue that honest piece revelation leads to social welfare in these peer-to-peer file sharing systems. And then we are going to show a new cryptographic primitive that we call randomized fair exchange, together with proofs of storage, incentivize honest piece revelation. So to better understand our results, we should interpret them this way. We are going to have cryptographic protocols that prevent malicious actions during exchanges, such that these incentivize honest piece revelation for rational entities. But for malicious entities, they can still over-report, under-report. We cannot do anything about that. Our model is a homogeneous network where peers proceed in rounds, and at each round, each peer may upload one piece and download one piece at most. And the reason for this is we want to focus on piece revelation strategies rather than bandwidth allocation issues. Now we are going to allow seeders to exist in the system, but they will not be part of our game theoretic model because seeders are irrational, altruistic entities. To better understand what is social welfare in this setting, let me represent the system as a matrix. So in this matrix, each row denotes a peer, each column is a round, and the cell values are the number of blocks downloaded by that peer at that round. Now, in the system we have m peers and the file has m blocks. So this particular matrix denotes an optimal scenario, where at each round, every peer downloads a block. And as you can obviously see, the average download time here will be m, which is equal to the number of blocks in the file. So this is optimal. The problem is, this optimal solution may not always be achievable. Consider, for example, a single seeder flash crowd scenario. So there is a single seeder in the system who has the complete file, and now suddenly n leechers join the system to download this file. Now, consider the following deterministic protocol. At round k, the seeder sends piece k to the first peer, P1. And again at round k, peer Pi sends piece k minus I to the next peer, Pi plus 1. So essentially, in the first round, P1 receives the first block from the seeder. Second round, P1 receives the second block from the seeder. And P1 uploads the first block to P2. So the parties proceed in a ring type of topology of this exchange. Each party sends a block to the next in the ring. Now, you can again observe that in this protocol, Pi finishes downloading at round m plus I minus 1, and this protocol has almost optimal uplink bandwidth utilization. So the only uplink bandwidth that is not utilized is the last peers, so it's not uploading anything to anyone. Now I want to mention two important issues here. One is that what we realize is that each scenario would require a different optimal solution, but overall, the social welfare would benefit from maximizing the number of one entries in this matrix. So if we maximize the one entries in this matrix, we are increasing social welfare. So we observe that to achieve social welfare, we need each peer to be matched with some interesting peer. And interesting here means that the peer has some block that the other peer doesn't have. And because this needs to hold for each peer, this matching needs to be done in a mutually interesting manner. And then of course, once the peers are matched, we want that the peers should be able to download a new piece. So we want that the peers are matched in a mutually interesting manner, and then they can download a new piece from each other. Now consider the following optimal global solution to the single-seater flash crowd scenario. Remember, in that scenario, the parties were exchanging pieces in a ring type of topology. So what we can do is, we can employ a ring topology multi-party fair exchange protocol, such that either each party in the ring obtains a block from the previous party, or no peer obtains anything. Now this would provide an optimal incentive, but this requires O(n) square communication per round for n peers. Therefore, we restrict our attention to pairwise peer-to-peer file sharing protocols. And by pairwise, I mean the following. So we have a matching phase that matches peers in pairs. And then these pairs of peers will continue with the exchange phase to exchange blocks. So these two steps, these two stages are repeated at every round. Every round consists of a matching phase followed by an exchange phase. The matching phase, just as in BitTorrent, uses these announcements. So every peer announces to every other peer the list of blocks they own and collects their announcements. And then the matching is pairwise, as shown visually here. And as I said, we allow seeders to be matched. Of course, seeders have no further interest. So in the matching of seeders, we cannot say we require mutually interesting matching, but for leechers, they must be matched in a mutually interesting manner. After matching, the peers will proceed with the exchange phase. So now what do we require from the matching phase? This can be done, let's say, by some distributed stable matching protocol, or actually BitTorrent's rarest first heuristic is shown to match mutually interesting peers, so maybe we can employ that as well. Regardless of how it is done, what we require is that the protocol must match mutually interesting peers, and it should match as many peers as possible. Why? Because remember, we are trying to maximize the one entries in the matrix representation of the system. Now, as long as this requirement is satisfied, how matching is performed will not affect our game theoretic analysis. Now, for the exchange phase, as I said, we modify the torrent files such that in addition to the hashes of the blocks, now there are tags of blocks to be used for the proof of storage scheme. So the exchange phase starts by both peers proving to each other the storage of the blocks. Remember, the announcements were done during the announcement, the matching phase. Now, each peer is proving that what they have announced, they indeed are storing. Then the peers proceed with a randomized fair exchange. And we can obtain a randomized fair exchange using 2 runs of coin tossing plus a regular fair exchange. So what do we do with the coin tossing protocols here? So in this protocol, we are going to pick a random block that is owned by this peer, but not owned by the other peer. So we will pick a random block that this peer has, but this peer does not have or did not report. So let's say this one is picked. Now we do the other way around. We will pick a random block among the ones owned by this peer such that it is not owned by this peer. So let's say we pick this one randomly. Now that the coin tossing is done, the parties proceed with a regular fair exchange of these blocks. Then this exchange finished, the round ends, the new round begins by the announcement of these new blocks, new matching phase, and new exchange phase. Now we are ready for our game theoretic analysis. Now consider an under-reporting peer. This peer may receive a block that she already has during the randomized fair exchange with non-negligible probability. Why? Let's say I have under-reported some block. So I have a block that I did not report. During the randomized fair exchange, I will obtain a random block that the other party has, but I did not report. So there's a probability that I will receive a block I already have because I did not report that block. And this probability is at least 1 over the number of blocks in the file. What about an over-reporting peer? An over-reporting peer will be called during proof of storage because I cannot prove storage of something I claimed, but I'm not storing. So as you can see in the matrix as well, both peers acting honestly is the equilibrium here. Why? Because as long as the matching was mutually interesting, both peers acting honestly, they will obtain a new block. So this is why we need this from the matching phase. The matching needs to be mutually interesting, and of course, as we said, by matching as many peers as possible, we are maximizing the number of one entries in the matrix. Unfortunately, there is not a great deal of related work in the social welfare in peer-to-peer file sharing systems. Indeed, it's an understudied field. I invite more researchers to work on this. There is Barbie and Fox that work for static sets of users. There is EquiCast that assumes join and leave rates are the same. There is Ratfish. It's a nice equilibrium protocol. Unfortunately, it requires a trusted third party to be involved in every exchange. And then there are two more types of related works I want to mention. One is that it is shown that fairness increases average download times. So there is a trade-off. But remember, fairness is a design goal for us to prevent free riding. So we are providing social welfare among fair protocols. And the other is, in terms of game theoretic related notions such as generalized prisoner's dilemma, there's a great deal of related work. If you are interested, I recommend reading our paper. So in conclusion, our solution is an equilibrium, and it provides social welfare in terms of uplink bandwidth utilization for a general class of protocols that we call pairwise protocols. And this is possible in a decentralized setting. We have a trusted third party, but it is not involved in every exchange. And it's possible due to a new cryptographic primitive we called randomized fair exchange, and can be achieved with constant computation, communication, and round complexity. As future work, we need better matching protocols and their analyses, maybe faster, optimized versions of exchange protocols, and of course an analysis in the heterogeneous network model. Thank you for your attention. If you have questions, I can answer now, or feel free to send me an email.
Thank you.